what is the SI unit of mass and how is it defined. So SI unit of mass is kilograms. The definition of SI unit of mass is given as kilogram is defined as the mass of platinum iridium block stored in the International Bureau of Weights and Measures in France. Thus, it is the mass of the international prototype of the kilogram. So you have this definition is also given in your textbook when we have spoken about significant measures. So basically you have the platinum iridium block which is stored in the international units of International Bureau of Weights and Measures, and that's in France. Next, we need to match the following prefixes along with their multiples. This is so basically the reason we have prefixes is because this is especially used when the SI unit is either too small or too large to depict the value that we want to show. So that's when we start using micro, milli, deca, hex, kilo, all of those, right? So these values or the table for these interconversions is also given in your textbook. So micro is 10 to the power minus 6. Deca is 10. Is 10 to the power 6. So this is the third one. Then giga is 10 to the power 9. And femto is 10 to the power minus 15. So these conversions are important and you can find that in your textbook. There's a table. So yeah, what do you mean, this is the 16th one, what do you mean by significant figures? So significant figures is nothing but the number of all the certain digits plus 1 which is doubtful. So it depends upon the precision and accuracy. All of these topics are covered in the video about uncertainty in measurement. And the uncertainty is either caused because of the human error or because the device or the apparatus which we are using has some uncertainty in it. So suppose we measure the volume of a liquid and we tell it's approximately 20.52 ml, sorry, 55 ml. This and this is certain, whereas this is uncertain. But this number has 4 significant figures. We had already covered the various concepts with regarding to the significant figures in the same uncertainty in measurement, where we learned how to identify, round up and do the various calculations to the significant figures. Question number 17. A sample of water was found to be contaminated with chloroform CHCl3, supposed to be carcinogenic in nature. The level of contamination was 15 parts per million by mass. So we need to express this in percentage by mass, and second we need to determine the molality of the water sample. So here, first of all, a carcinogenic substance is something which can lead to cancer. And chloroform previously was actually used as a anesthetic, but over time they realized that it was not a good option because of its carcinogenic nature. Now here you have the word ppm. ppm means parts per million, which means the mass of that particular substance. This is especially used for very less quantities, and the mass of that particular substance is 15 parts of chloroform is present in 10 to the power 6 parts of the water by mass. Okay, so percentage by mass of CHCl3 is equal to 15 divided by 10 to the power 6, because you have 10 to the power 6 parts. You have the total amount of parts is 10 to the power 6, and the number that was contamination is 15, and this is multiplied into 100. This is just weight percentage calculation. When this is simplified, we get 1.5 into 10 to the power minus 3%, which means in 100 of that sample you will have 1.5 into 10 to the power minus 3% or minus 3 of chloroform. Okay, so we are basically calculating the percentage by mass. Next, we have to calculate the molality. So molality is to do with the number of moles divided by its mass. So you have molar, first let's calculate the molar mass of CHCl3. So here you have carbon whose mass is 12. You have only one atom, so just 12 plus 1, which is for hydrogen, and chlorine is 35.5, and this has to be multiplied by into 3 because of 3 atoms of chlorine present. So this is simplified to give us 110.5 as the molar mass, so grams per mole. Now, to calculate the moles of CHCl3, we have to divide the number of moles, the molar mass, and the percentage by mass. Here we are taking the percentage by mass of CHCl3 because we are assuming 100 parts. We are taking in 100 parts of water, and in 100 parts of water, we know that 1.5 into 10 to the power minus 3 is the mass of CHCl3. So number of moles will be equal to 1.5 into 10 to the power minus 3 divided by 110.5 grams per, and this will be in grams per mole. So grams will get cancelled, and this we will get it as 1.255 into 10 to the power minus 3 mole. And since we have taken mass of water as 100, mass of water is 100. Okay, so in 100 grams of water you have 1.5 into 10 to the power minus 3 grams of chloroform. Based on that only we were able to calculate the number of moles. So molality, which is denoted with the small m, is equals to 1.255 into 10 to the power minus 5 divided by 100, and this is multiplied into 1000 because in the definition of molality it's supposed to be, the mass is supposed to be in kilograms, but here we have only taken grams. So we are multiplying it with 1000 to show the conversion of this value from grams to kilograms, and when this is simplified we get 1.255 into 10 to the power minus 4 molal. So first we had been asked to calculate the percent by mass of chloroform, and this was calculated simply by using this formula, because here you have 15 parts per million, that's why we're dividing it by 10 to the power 6, which this basically means that 15 parts per million ppm means 15 parts of chloroform is present in 10 to the power 6 parts of the solvent. So molality we calculated by using the formula molality equals to number of moles divided by the mass of the solvent in kilograms, but this value was in grams, so we just multiplied it with 1000. So first we had to calculate the molar mass, which is done simply by adding the individual atomic masses, and then we had calculated the number of moles. Since we are assuming the mass of water is 100 grams, then 100 grams of water will have 1.5 into 10 to the power minus 3 grams of chlorophyll. So we just divided these two values, that is the mass divided by the molar mass will give us the number of moles, and then all of this was just substituted in the equation, and then we got the answer for molality. To understand more about molality, do check out the video. Question number 18. Express the following terms, or rather the following, in scientific notation. So scientific notation has this thing is 10n into 10 to the power n, where this n is the number with a single non-zero digit before the decimal point, and this n is the number of places the decimal point has to move. So if it is a plus value, the decimal point moves to the left. When it's a minus value, the decimal point moves to the right. So when we have this question where we have to convert all of these into a scientific notation, and n will have a one non-zero digit in front of the decimal point. So following that rule, here 0.0048, the decimal point is shifted to the right by 1 and 2 and 3 points. So 4.8 into 10 to the power minus 3. Here you have 234 and then you have followed by 3 zeros. Okay, so here assuming here is the decimal point, it is moving to the left by 1, 2, 3, 4, 5 points. So this becomes 2.34 into 10 to the power 5 because it moved to the left. When it moves to the right, when the decimal point is moving to the right, it gets a minus sign. Similarly, here also it is moving to the left. So 1, 2, 3. So 8.008 into 10 to the power 3. Next, here you have 500 and it's moving to the left, of course. So 1, 2. So 5 into 10 to the power, or rather better put as this 5 because this shows the accuracy. 5.000 into 10 to the power 2. Next, the last one here, it is already, and it's significant, it is already its scientific notation, so it can be left like this, or you can also write it as 6.0012 into 10 to the power by 0. So anything to the power 0 is equal to 1. So we are just merely multiplying. So you can leave it at this also. So it's alright. So even if you write 6.0012, it is correct only. Next one. How many significant figures are present in the following? So there are certain rules and regulations that are followed. I will just read them once. So first one is all the non-zero digits will be significant. The second, zeros before the first non-zero digit is not significant. Zeros in between two non-zero digits are significant. Zeros at the right of the number are significant only if they are on the right of a decimal point. So this will show how accurate a particular measurement is. So here you have zeros before the first non-zero digit. So these 3 zeros are not significant. So you have only 2 significant figures in this number. Next one, the 0 between 2 non-zero digits are significant. So 1, 2 and 3. Same goes for this as well. 5005. You have 1, 2, 3, 4. 4 significant figures. Now here you have 1, 2, 3, but the zeros on the right are significant only if they are after the decimal point. This means these zeros are not significant, but this 0 over here is significant, which means the number of significant figures over here are 4. The next one, 2.0034, it has 5 significant figures. Now we need to round up the following up to 3 significant figures. So which means we need to have only 3 significant figures. And this is done by rounding up methods. You have certain rules and regulations. While we solve this, I'll go over them. So here 1, 2, 3. This is going to be our number. And since this number is below 5, the digit stays the same. So 34.2. Now 10.041 becomes 10.4. Similarly, here also you have this digit less than 5, which means it will not change the value of this one. Now here we need to calculate the, first of all, these two zeros will not be considered significant. So Here this is the number which is being removed, and because it is more than 5, this number changes, this big number becomes plus 1. Okay, and because it is 50, it is 9 becomes 10, so it becomes 0.0460. Here when this number is removed, because it is more than 5, the previous number gets added by 1, and because it's a 9 over here, obviously 59, so 60. Okay, the last one, 2808, similar to the previous one. Here you have 4 significant figures. If it has to become 3 significant figures, this changes the value. When this is removed, this becomes plus 1, so 2810. Do check out the video which was done regarding the scientific notation and significant figures and rounding up of significant figures for a better understanding of these.